Welcome to Section 7, Lesson 1. Across the past 6 sections, we built linear equations, inequalities, exponents, radicals, functions, and systems of equations. Section 7 introduces polynomials, the next major class of algebraic objects after linear expressions. Polynomials sit at the heart of algebra and the rest of mathematics. Every smooth function can be approximated by polynomials. Every linear and quadratic and cubic equation comes from a polynomial, and most of the equation solving an expression manipulation work in algebra and calculus is polynomial work in disguise. Today we lock in the formal definition of a polynomial, the anatomy vocabulary, the standard form, and the classification scheme by degree and by number of terms. By the end you will recognize a polynomial, identify its leading coefficient and degree, and know how to write any polynomial in standard form for downstream computation. First idea on the board. A polynomial in one variable x is a sum of terms, where each term has the form a times x raised to a non-negative integer power. Examples include 3x squared plus 5x minus 7 and 10x cubed minus 4x plus 1, and even just a constant 5, which is technically a polynomial of degree 0. Counter examples that are not polynomials include x to the negative 1, which has a negative exponent, x to the 1/2, which is a square root and a fractional exponent, and 1 over x, which is the same as a negative exponent. The non-negative integer exponent rule is what makes the object a polynomial. Second idea, the anatomy of a polynomial uses 6 terms of art that you must memorize: term, coefficient, leading term, leading coefficient, degree, and constant term. A term is one of the additive pieces, like 5x squared. The coefficient of a term is the numerical factor, like 5 in 5x squared. The leading term is the term with the highest exponent. The leading coefficient is the coefficient of the leading term. The degree of a polynomial is the highest exponent that appears, equivalently the exponent on the leading term. The constant term is the term with no x at all, equivalently the term with x to the 0. Memorize the 6 pieces of vocabulary and use them deliberately on every polynomial problem. Third idea. The standard form of a polynomial writes the terms in descending order by exponent leading term first, then the next highest, and so on, ending with the constant term. Standard form is the universally agreed convention. Every textbook, software package, and homework problem uses it. Classification by degree gives names to small polynomials. Degree 0 is constant, degree 1 is linear, degree 2 is quadratic, degree 3 is cubic, degree 4 is quartic, degree 5 is quintic. Classification by number of terms gives names to: 1 term is a monomial, 2 terms is a binomial, 3 terms is a trinomial. Higher term polynomials are simply called polynomials with no special term, count name. A polynomial in one variable x is a finite sum of terms, where each term has the form a sub n times x raised to a non-negative integer n. The sequence of coefficients a sub 0, a sub 1, a sub 2, and so on may include zeros, but the exponents must be non-negative integers without exception. Examples that are polynomials: 3x squared plus 5x minus 7 is a degree 2 polynomial with leading coefficient 3. 10x cubed minus 4x plus 1 is degree 3 with leading coefficient 10. The constant 5 alone is a degree 0 polynomial, sometimes called a constant polynomial. Even the 0 polynomial is a polynomial, though by convention its degree is undefined or sometimes negative infinity. Counter examples that are not polynomials. The expression x to the negative 1 is not a polynomial because the exponent is negative. The expression x to the 1/2, also written square root of x, is not a polynomial because the exponent is fractional. The expression 1 over x is the same as x to the negative 1 and is not a polynomial. The expression 2 to the x is not a polynomial because the variable x is in the exponent rather than the base. The 6-piece anatomy vocabulary. Term 1 additive piece. Coefficient the numerical factor of a term. Leading term the term with the highest exponent. Leading coefficient the coefficient of the leading term. Degree, the highest exponent that appears, equivalently the exponent on the leading term. Constant term, the term with no x at all, equivalently the term with x to the 0. Use these 6 words deliberately on every polynomial problem. Standard form writes the terms in descending order by exponent to leading term first, then next highest ending with the constant term. Classification by degree 0 is constant, 1 is linear, 2 is quadratic, 3 is cubic, 4 is quartic, 5 is quintic. Classification by term count, 1 is monomial, 2 is binomial, 3 is trinomial. Higher term polynomials simply called polynomials with no special name. Today we drill this vocabulary on 2 worked examples and lock it in for the rest of the section. Here is the worked example. Identify all 6 anatomy pieces of the polynomial p of x equals 4x cubed minus 7x squared plus 2x minus 9 and write it in standard form and classify it by degree and by number of terms. Step 1. Identify the terms. 4 terms total 4x cubed, negative 7x squared, 2x, and negative 9. Each term has the form coefficient times x to a non-negative integer power. Step 2. Identify the coefficients of each term. The coefficient of x cubed is 4. The coefficient of x squared is negative 7. The coefficient of x is 2, equivalently x to the 1. The constant term has coefficient negative 9, equivalently negative 9 times x to the 0. Step 3. Identify the leading term and leading coefficient. The leading term is the term with the highest exponent, which is 4x cubed. The leading coefficient is therefore 4. Step 4. Identify the degree. The degree is the highest exponent that appears, which is 3, so this polynomial has degree 3. Step 5. Identify the constant term. The constant term is the term without any x, which is negative 9, equivalently the value of p at 0, since plugging in 0 kills all the x terms. Step 6. Write the polynomial in standard form. Standard form is descending order by exponent. The polynomial is already given in descending order 4x cubed minus 7x squared plus 2x minus 9. Already in standard form, no rearrangement needed. Step 7. Classify by degree and term count. Degree 3 means cubic. 4 terms means it has no special term count name beyond polynomial. Only 1 term, 2 term, and 3 term polynomials get monomial, binomial, and trinomial names. So the full classification is cubic polynomial with 4 terms. So the anatomy pieces are 4 terms, leading term 4x cubed, leading coefficient 4, degree 3, constant term negative 9, standard form already met, classification cubic polynomial. The big lesson from this example is that polynomial anatomy is mechanical vocabulary application. Identify each piece by definition, no judgment calls. The vocabulary is the foundation for every polynomial operation in the rest of section 7, so lock these words in deliberately. Here is a second example. Decide whether each expression is a polynomial. If yes, write it in standard form and classify by degree and term count. If no, explain why. 5x squared minus 3x plus 2. All exponents are non-negative integers, so this is a polynomial. Already in standard form, descending order by exponent. Degree 2, 3 terms, so it is a quadratic trinomial. Expression 2. 6x to the negative 2 plus x. The negative exponent disqualifies this from being a polynomial. Negative exponents are not allowed in polynomial definition, so the expression is rational rather than polynomial. Expression 3. 7x to the 1/2 plus 4. The fractional exponent x to the 1/2 is the same as square root of x, which is also disqualifying. So this is not a polynomial. It is a radical expression, which we covered in section 10. Expression 4. 8x cubed plus 0x squared minus 6. The middle term has a coefficient of 0, which is the same as not having that term at all. All exponents are non-negative integers, so this is a polynomial. After dropping the 0 term, it is 8x cubed minus 6x. Already in descending order, standard form complete. Degree 3, 2 terms, classification cubic binomial. Expression 5. 12, just a constant. A single constant is a degree 0 polynomial. also called a constant polynomial. One term, so it is a constant monomial. Expression 6, 2 to the x plus 3. The variable x is in the exponent, not the base, so this is not a polynomial. It is an exponential expression, which we covered in section 12. Summary expressions 1, 4, and 5 are polynomials of various types. Expressions 2, 3, and 6 are not polynomials due to negative, fractional, or variable exponents. The big lesson from this example is the disqualification rules. Anything that puts the variable in a negative power, fractional power, or in the exponent itself is not a polynomial. The non-negative integer exponent rule is the only structural rule that defines the polynomial class, and applying the rule rigorously sorts any algebraic expression into polynomial or non-polynomial in seconds. 3 mistakes that catch every algebra student during their first weeks of polynomial work. Each one is fixable with a small explicit habit applied on every problem from now on. First mistake, confusing term with coefficient when reading polynomial anatomy. A student looks at 5x squared and says the coefficient is 5x squared, when actually the coefficient is just 5. The term is 5x squared as a whole. The coefficient is the numerical factor only. The fix is to internalize the definitions cleanly. Term equals coefficient times variable power. Coefficient equals just the number. Variable power equals just the x to the in piece. 3 separate words for 3 separate pieces applied consistently on every polynomial problem. Second mistake, dropping the negative sign when reading the coefficient of a subtracted term. A student looks at minus 7x squared and reports the coefficient as 7, when actually the coefficient is negative 7. The minus sign is part of the coefficient, not separate from it, because subtraction is the same as adding a negative. The fix is to mentally rewrite every subtraction as adding a negative before reading off coefficients. 3x squared minus 7x rewrites to 3x squared plus negative 7x, and now the coefficient of x is unambiguously negative 7. Third mistake, mistaking a radical or rational expression for a polynomial. A student sees square root of x plus 3 and assumes it is a polynomial, when actually the square root of x is x to the 1/2, which has a fractional exponent and disqualifies the expression from polynomial status. Or a student sees 1 over x plus 2 and assumes polynomial, when 1 over x is x to the negative 1 and disqualifies the expression. The fix is to convert every expression to exponent form first, then check the exponent rule. Every exponent must be a non-negative integer, otherwise the expression is not a polynomial. Polynomials show up across data analysis, physics, engineering, computer graphics, and approximation theory continuously. 4 broad sectors below where every working professional uses polynomial machinery routinely. In data analysis and statistics, curve fitting through measured data points uses polynomial regression. The ordinary linear regression you might know is the degree 1 case. Degree 2 regression fits parabolas through scatter plots. Higher degree regression fits more complex curves. Polynomial regression is one of the foundational techniques in statistical modeling, machine learning, and experimental science, and the polynomial vocabulary you learn today is the language used to describe every regression model. In physics and engineering, projectile trajectories under gravity follow degree 2 polynomials. Position equals initial position plus velocity times time minus 1/2 dt squared. Beam deflection under load is described by degree 3 or 4 polynomials. Signal processing uses polynomial filters. Control theory uses polynomial transfer functions. The polynomial structure is everywhere in physical modeling, and the vocabulary from today is what physicists and engineers use to describe their models. In computer graphics and animation, Bezier curves and B-splines are piecewise polynomial approximations of smooth curves. Every curve drawn in Adobe Illustrator, every animation path in After Effects, every smooth surface in 3-dimensional modeling software is a polynomial spline. The mathematics of polynomial curves was developed in the 1960s for automotive design and is now the foundation of every digital graphic on every screen. In approximation theory, Taylor series approximate any smooth function with polynomials. Sine, cosine, exponential, and logarithm are all approximated as polynomial sums in calculators and in numerical libraries. The fact that polynomials can approximate any smooth function arbitrarily well, the Stone-Weierstrass theorem, is one of the foundational results of analysis. Polynomial approximation is therefore the backbone of all numerical computing, from spreadsheets to scientific simulations to machine learning models. 3 things to take with you from this lesson today. Polynomials are the next major class of algebraic objects after linear expressions, sitting at the heart of algebra and the rest of mathematics. Today's vocabulary is the foundation for the entire Section 7 curriculum on polynomial operations and equation solving, and you should be very comfortable with every word of the anatomy vocabulary by the end of this very first introductory lesson of the section. First, a polynomial in one variable x is a finite sum of terms, where each term has the form coefficient times x raised to a non-negative integer power. The non-negative integer exponent rule is the one structural rule that defines the polynomial class. Anything with a negative exponent, fractional exponent, or variable exponent is automatically disqualified from being a polynomial and belongs instead to a different class of expression like rational, radical, or exponential. Second, the 6-piece anatomy vocabulary is term, coefficient, leading coefficient, degree, and constant term. A term is one additive piece. The coefficient is the numerical factor with sign included. The leading term is the term with the highest exponent. The leading coefficient is the coefficient of the leading term. The degree is the highest exponent that appears. The constant term is the term with no x at all, equivalently the value of the polynomial at 0. Memorize and apply these 6 words mechanically on every polynomial. Third, standard form writes terms in descending order by exponent, leading term first ending with constant term. Classify by degree. 0 is constant, 1 is linear, 2 is quadratic, 3 is cubic, 4 is quartic, 5 is quintic. Classify by term count. 1 term is a monomial, 2 is a binomial, 3 is a trinomial. Higher term polynomials are just polynomials. Coming up next, the lesson called Adding and Subtracting Polynomials, which applies the anatomy vocabulary from today to the simplest polynomial operations. Term by term combination using the like terms rule from way back in section 1 is essentially the entire mechanic, and the lesson teaches the fast and accurate algebraic technique.